Hello everybody. So today I'm going to be talking about supersymmetry because I looked on YouTube and I could find no video, giving me details about what supersymmetry is, only just like cartoons that say, oh, it relates to bosons to fermions. But really supersymmetry is much deeper than that and much more interesting, and hopefully I can convey it to you today. So supersymmetry deals with combining two types of symmetries. So we have the space-time symmetries, and that is just symmetries that are Poincare invariant, which in other words, they abide by the Lorentz transformation, and they have translation to them. And then we have something else called internal symmetries. And for example, so they thought once upon a time that the neutron and the proton were related. So in a nucleus, we have the neutron, we have the proton, we have the electron. And these are just actually composite particles made of quarks. So you have up, up, down, 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 up. And they thought they were similar because of the mass was very similar, not exact, but similar. So they have, so this is SO3, 1, the symmetry group. And then they thought that you could just rotate, have like a rotation to get from a proton to a neutron. So, such as this is just standard SU2 rotation. So just like cosine theta, sine theta, sine theta, cosine theta. And now they wanted to, for various reasons, such as a hierarchy problem, they wanted to combine these two and make them into one group. But Sidney Coleman and Mendula in the 60s ruled this out, and they used commutation relations. Which was indeed their fallback. So the real answer was that anti-commutation relations come into the picture, but really the solution to get these two in one symmetry group is something that was called the minimalistic supersymmetry extension of the standard model. And so before I go into the mathematical detail, I'll just briefly tell you what this is, the extension. So we have particles and superparticles. And pretty much what in this operation we just take. We assign each particle with a super partner. And then if the particle is a photon, or a particle is a boson, the super partner would be a fermion, and vice versa. So we could just see this now. So we have the photon, it's spin 1, and then its super partner is the super partner of the photon, phonion, and that's actually just spin 1/2. The electron is spin 1/2, and the selectron is spin 0, and then we just do this for other particles too, like the W boson. That is spin 1, and then its supersymmetric partner, the wino, is spin 1/2. And then the Higgs boson spin 0, it's super partner, the Higgs-Zeno, and that's spin 1/2. And you keep on going, the gravity, graviton, that's another interesting one that is unique to this matching. That's 2, this one is the gravino. This is the phonino, gravino, 3/2. Okay, so now we could look at, what is causing these, what generates these. So for regular QFT, in 3+1 dimensions QFT, we have the generators for the Lens transformation, which is anti-symmetric. And we have the generators for translations, P mu, Hamiltonian P mu, just P vector. So that's translations. And now what generates the supersymmetric extension is something called supercharges, which are like regular charges in the sense. So our supercharge we could define by this anti-commutation relation now. QB, and that's just to the Dirac gamma matrices, which we encountered in the Dirac video. If you haven't seen that, I'll just post it because it's very quick, short, very insightful video. I tried to minimize what is the Dirac equation, very simple terms, and I feel personally like I did a good job succeeding. So the gamma matrices and then P mu. So now let's talk about what these supercharges actually do, and that is, sure, I'll erase it. So just keep on reverting back to strain. So pretty much all you have to remember that there's bosons go to fermions, fermion goes to bosons, and that translation is what these supercharges are meant to do. So if we could define the boson, fermion for the boson, the upper component of the state, and for the fermion, the lower component. This is actually interesting when you think about it, because normally we would say this is spin up, spin down, or in the Dirac equation, right hand moving, left hand moving, but these are actually two different types of particles. And the supercharge, what it does when it acts on the boson, it turns it into a fermion. And then likewise, the fermion goes up to the boson. So Q. And these supercharges, they're operators, but they're also spinners, and they carry charge, spin 1/2, which is why I kind of regretted deleting this table, erasing it, so you could see, but it's all good. So, and this goes to a boson. And there's also, it's called something like the parity operator, or just, it just tells you, very similar to the projection operator. So I think it is, quote me if I'm wrong, but I plan on saying this, but now I'm in the mood to say it, so I'm gonna say it. So this is fermions, it's -1, and bosons, +1. So if we act this operator on a bosonic state, so it's Q psi B, this turns into a fermion, so this is just minus F. And then, likewise, my handwriting's getting a little sloppy, I'm going a little crazy here. So minus 1F, Q, F, B, and then that is just positive. Coolio, so that is what I have for you today. I can make a video on going into more detail about applications of supersymmetry. So Ed Wooden made a toy model going from QFT to just defining the superalgebra in regular quantum mechanics, and that is easier to understand. I have yet to understand how supersymmetry plays a role in QFT, because I have not gotten that far in QFT yet, but the supersymmetric version of quantum mechanics is actually really interesting, and yeah.